Okay. Cool. Yes, actually, before we begin, let me clarify one of the doubt he asked in last class. So, I forgot to discuss it at the end of the class. So, let's say you have first order RC circuit. Okay, so let's say give the input as a periodic square wave going from say 0 to 1 volt. What is the average voltage across the capacitor? Why do you say it's half?
RC is greater than because in the average case there will be no current through.
Right? I mean, yeah, the argument is this, right? I mean, in steady state there cannot be any DC current flowing through the capacitor, else the voltage will keep blowing up. So the DC current through the capacitor is basically the DC current flowing through the resistor. So if I call the capacitor voltage as VC, the DC current through the resistor is what? The average input voltage minus average capacitor voltage by R, and this is 0. So which means capacitor average voltage will be the average of A irrespective of RC, right? There is no assumption made on the time constant RC. In steady state, the average will still be around 0.5. That's fine. But I mean, this you can do if you have an LTI circuit like this. But say the circuit we considered in the last class. So that was an LPTV circuit, right? So even here in steady state, the average current flowing through this capacitor is 0, right? And this current will be equal to this current, let us say. And but the problem is now, if I were to write the average current flowing through the resistor, this is not simply V in average minus capacitor average by R, right? Because you know that this is an LPTV circuit, DC current, that is a current at a frequency F equal to 0, will not only be due to the voltage at the same frequency DC at F equal to 0, but it will also have DC currents due to voltages at multiples of Fs. So you can no longer write like this, it will be plus something. Okay. So this is still equal to 0, but this will not give you an information to directly find what is this. Whereas for LTI circuits, you can do it like this because you know a current at DC will only be due to a voltage at DC. Is that fine? Cool.
You wrote IR average is equal to the current that is flowing through the capacitor.
I mean, to the entire capacitor network. Let's say this plus this, right? Yeah. Okay.
Here the capacitor, the voltages that are causing the issue are VC average. That is
what you want to find, let us say.
Correct. So I am saying that here the input is not from the input side there is no time variance, but at the output side the time variance is causing a problem back at the at that node. It's forcing some time variance back at the
here the time variance is causing some changes here.
First circuit, if a network is LTI network,
if any
given network,
right, yeah.
If I delete it as a periodic square,
okay,
then any branch voltages will be the proportional at average value of DC.
I didn't get it. So I mean, let's say you're giving a periodic square wave to some LTI network.
Yes.
Okay. What's your question?
In this case, the average number of input is half.
Right.
And same average is current the output.
Yeah, I mean, this is because the average current through the capacitor is 0 and the average current through the capacitor is same as the current flowing through the resistor. In this particular case, these two currents are equal, right? So if this average current here is 0, the average current here is also 0, and that gives you this relation. And that is why capacitor voltage is equal to the input average. For other cases, you'll have to work out. I mean, the average current through a capacitor is 0 in steady state. That is always true. And
Taking the same network in another cascade, RC.
one more RC. Okay. Yeah, it will still be same. Average current through these capacitors are 0. You again write KCL, right? I mean average voltage. I mean you work it out, right? The average currents in these two capacitors are 0 still. From that you find out if you can get any information about these two. You will be able to.
So in LTI network, current to the average current to the current is 0.
No, it's not an LTI network. In any network, the steady state average, in steady state, the average current through capacitor is 0. As long as the circuit doesn't, is stable and voltages don't shoot up to infinity.
In that case, we can find out.
Yeah. This is given in steady state. If the circuit voltages are not constant, it's not infinity, the average current through the capacitor and average voltage across inductor is 0. That is always true. And how you can use it to find whatever you need is dependent on the circuit you have. Okay. Okay, so now let's move on to the topics we were discussing. In the last class, we looked at variations of Tellegen's theorem. So the idea here is basically if you take any two electrical networks, say I have a network N, I have another network, I'll call it N hat. As long as these two networks have the same graph, right, that is they have the same number of nodes, same number of branches and identical connection between the nodes. And if the branch voltages and currents here are Vk and Ik, and here it is Vk hat, Ik hat, we saw that summation over all the branches, voltage in the first network multiplied by the corresponding branch current in the other network is 0. So this also is equal to Vk hat Ik, and this is also equal to Vk Ik and Vk hat Ik, right? And of course the last two you already might be knowing, and this is a simplified form of Tellegen's theorem, that the last two terms are 0, and this is an extension of Tellegen's theorem, where although it might be puzzling at first, we saw with an example that why this makes sense. And please recollect, the only thing that needs to be satisfied to get this result is what? Is only KCL and KVL. So basically any lumped electrical network where KCL and KVL are valid, you can basically apply this. Okay. And of course, it's not necessary that the two networks need to be similar. That is, this can be LTI, this can be time varying, non-linear, anything, right? And we also extended it, and we saw that if the voltages and currents are varying with time, we can look at the voltages and currents in the first network at T1 and the second network at a time t equal to T2, so that gives you this Ik hat of T2. This is basically equal to Vk hat of T2, Ik of T1, and so on. You can write the rest. Okay. And using this Tellegen's theorem, we proved or looked at the principle of reciprocity, and we looked at the case for a network containing only linear resistors. So let's say we have a network containing only linear resistors. If I apply a voltage at this port 1, I'll call 1 prime. So this voltage is V1. This is 2 prime, and I measure a voltage here V2. Now I can get the same response by taking the same network, by applying a corresponding excitation at the second port and measuring a response at the port 1. So what should be the excitation I should apply here? It's a current source, and what should I measure here? It's a current, we have to short circuit, right? And the basic, the thing was, even if you null the excitation sources, basically if you null the excitation source here, the port behavior at these for these two networks must be same. And similarly, if you null the excitation source here, this behaves like a short, and that's what you have here. Okay. And the result you have here is basically V2 by V1, the same as if I call this I2 hat and I1 hat, I1 hat by I2 hat, and this comes about if you use Tellegen's theorem. So let me just write it quickly. So we use the fact that summation k Vk Ik hat is Vk hat Ik, and we'll have to do it for all the branches. If you do it for this branch, what we have is the voltage V1 times the current I1 in this direction, this I1 hat, plus Vk Ik hat for the internal branches, plus in this branch the voltage is V2 times the current in this direction minus I2 hat. This is equal to the port voltage, the branch voltage here, that is 0, so this becomes 0, plus the product for the internal branches, plus say this voltage is some V2 hat times the current here, which is 0, so this simplifies like this. And in the network we considered, since it has only linear resistors, the branch voltage you can write it to be the corresponding branch current times some equivalent resistance. So the same can be done here as well. So this means that these two terms cancel each other, and you finally end up only with these two, and this gives this result, right? And the important thing to notice, the reason why we are able to get this result is because this summation for the internal branches, they cancel, right? So summation k Vk Ik hat is equal to summation k Vk hat Ik for the internal branches, and one way to satisfy this condition is if you have the branch voltage to be proportional to the corresponding branch current, right? And this is a case where we applied a voltage and measured the voltage. We also looked at the other three combinations, and again the rule is simple. You make sure that even if you null the excitation source, the port behavior in the two networks are similar, right? So let's say I take this case. So ideally here I should be applying a current here and measure the current. But let's see what happens if we try to apply a voltage here and measure a voltage here. Right? So let's see if what happens to this, right? If this is really equal. So again we'll do the same thing. We'll apply Tellegen's theorem. So for this branch we have V1 times the current here 0, plus of course internal branches cancel off, I will not write it, plus here we have V2 times current in this direction, say that's some I2 hat. So this is equal to the voltage in this branch times the current in this branch. So this is some I1, this V1 hat I1, plus of course the internal branches that anyways get cancelled, plus V2 hat times the current here 0. So what do you get finally? You get V2 by I1 V1 hat by I2 hat. Right? So what this says is the excitation at the input must be a current here. Right? If you apply a current I1 here in this direction and measure the voltage here, that will be equal to the voltage you measure here if you apply the same current I2. Right? So the excitation here should not now be a voltage. So the result we get is this has to be a current. Right? And similarly here this should not be a voltage. Right? Denominator is the input quantity. So basically I should be exciting with a current. And of course I can interchange the currents in the two. So I'll just see the current direction is like this. And this is what was one of the cases for reciprocity, where you apply a current in one port, measure the voltage in the other port. The ratio of these two will be equal to the same ratio of the voltage you apply in the first port in response to a current at the other port. Right? So, and similarly for the last case where we had voltage input and a current output. So what should be the excitation here? What should be the excitation here? It's a voltage, right? Because if if I null it, this should be a short. So this should be a voltage, and what should be the quantity I measure? It's a current. Right? So I'll use the summary I got here. So of course if I call it I1 and this is V2, I2 hat and V1 hat. So here V2 by V1 will be same as V1 hat by I2 hat. So this is V1 V2 and I2 hat and I1 hat. Oops, this is V2 by I1. So right. For the second case, the ratio of V2 by V1 will be equal to I1 hat by I2 hat. In the third case, I apply a current and measure the current here. Here I will apply a voltage and measure the voltage. So that gives this relation. And the last is where I apply a voltage, measure the current. And this is what we get. Okay, cool. And yeah, this is again valid only if we can cancel the summation Vk Ik hat and Vk hat Ik for the internal branches here, right? And for the example we have chosen, that is happening because the branch current is proportional to the corresponding branch voltage, right? So this is good, but we just have considered a network which contains only resistors, so this is still boring. So to make it interesting, let's say we consider a network containing capacitors and inductors as well. So now this is a network containing linear RLC. So what do you think? Will reciprocity be valid or not valid? Sorry? No, there is nothing to do with bilaterality here. Yeah, but I mean, we wanted, if you take, exactly, right? I mean, so let's say I excite something here, this is the input and output. If I take the same network, I apply a corresponding input excitation here and measure the output. And this will be valid only if for the internal branches, this is equal, right? And for the resistor case, we were able to get it because Vk was Ik times Rk. So for capacitor, let us say, can you write the voltage to be current times something? Huh? Sorry? Yeah, basically, I mean, in time domain it is this, you cannot write it, right? It's 1 by c integral Ik of d dt. But if you go to frequency domain, this is some impedance Zk times this, fine. So basically, instead of applying Tellegen's theorem in time domain, where we did this V1 times I1 hat in time domain, we apply it in the frequency domain, then you can still prove this, right? Let me just copy paste. So she was mentioning
in the application of reciprocity, we never assume time variance.
no, we'll come to that slowly. This, I mean, okay, for resistors we didn't assume anything, but if you were to write this,
Because when we are converting it into frequency domain,
exactly,
there is an inherent assumption there.
exactly. I mean, this is where we have assumed that it is time invariant, right? Because this capacitor I assumed it to be constant, right? I mean, please recollect, if only for an LTI network I can write it like this. For an LPTV network we can only write in terms of the matrices. Okay. So yeah, as he mentioned, here is where I assume that it is an LTI capacitor, right? And that is why I can write the relation like this. If the capacitor is varying with time, this relation is not complete, right? Because you know that Q of t is now C of t times V of t. So you integrate it and exactly, so you will have something. Fine. Yeah, so this case we'll do it in frequency domain, so everything will be function of frequency, right? So the result you get will also be same. So let me erase this portion. So now the internal branches will have Vk of j omega to be some Zk of j omega times Ik of j omega. That's all. And here also it's the same. Ek hat of j omega is some Zk of j omega times Ik hat of j omega. Right? And the moment you do, you will still have this relation to be valid. But the point to notice, it is valid if you look at the Fourier transforms, that is in frequency domain. Okay. So the result we have, if you have inductors and capacitors, the linearity is applicable only in the frequency domain. So the ratios will be equal only in the frequency domain. Okay. So please bear in mind, so this doesn't imply V2 of t by V1 of t is equal to I1 hat of t by I2 hat of t. In time domain, this ratio is not equal. Right? So in time domain, what is the relation that is valid? From here, you see? I mean, we know that this is the relation in frequency domain. In time domain, this ratio is not valid. So what is the relation that holds good? If you look at the voltages and currents in time domain. Yeah, so basically you take the product, right? I mean, V2 of j omega times I2 hat of j omega is I1 hat of j omega times V1 of j omega. So in time domain, it is V2 of t convolved with I2 hat of t. That will be I1 hat of t convolved with V1 of t. Is that fine? So please bear in mind, the moment you have impedances, that is inductance and capacitance, the ratio will be equal only if you consider the transformed quantities, not the time domain quantities. Cool. And in the time domain, the relation that is valid is this, right? So let us say you don't know about a Fourier transform. Okay. So say you live in some alternate universe where Fourier was busy in politics and he didn't have time to invent Fourier transform. I mean, in fact, he was a politician. I don't know if you know it. Anyway, so let's say you don't know about Fourier transform. How will you prove this? The only thing we know for sure is summation k vk ik hat summation k vk hat ik, or we write it here. We saw this is true. vk of t ik hat of t is vk hat of t ik of t, right? And if you think about it, to get this result in frequency domain, we use the fact that vk of j omega times ik of j omega is that is, we apply the Tellegen's theorem in the frequency domain, but say you don't know frequency domain, right? Yeah, I mean, so this is in time domain. What does it imply? This is where we started to prove reciprocity in frequency domain. So if this is equal in time domain, what does it imply? It's convolution. So ik hat of t. Okay, I mean, but we only know this, right? From here, we need to prove this, right? Because the moment we know this, we can prove this. We know Tellegen's theorem for the product quantities, right? Vk into ik hat, that we know. But for proving this reciprocity for capacitors and inductors, we need to prove this. Only then we'll have everything in terms of convolution. Is that fine? So how do you think we can prove it? Basically, this is what, this is what we have, we know. This is what we know, and we have to prove this result. So, any idea?
So implication of current, so
No. I mean, this can be true. I mean, this is for any linear network. You are considering only for a case of capacitor. I am saying
We can use the fact that time variance, like one network at t and another network at different time.
that's a good starting point, right? I mean, we know that Tellegen's theorem is also valid if you take the currents and voltages for the two networks at two different times. So for the voltages Vk and Ik, I'll take them at a time t1, and for Ik hat and Vk hat, I'll consider a time t2. So I mean, first let's expand this, right? This is what we know. We need to prove this. So if this is true, what is true? This is basically integral Vk of t minus tau eta integral Vk hat of t minus tau so we know this. So what do you think should I choose my t1 and t2 so that we get closer to this? This is what now we have to prove, right? And we know that this is true. We saw it in the last class. So compare the two equations and tell me what should the values of t1 and t2 so that we are at least one step closer to what we need to prove. Yeah, so you choose t1 to be t minus tau and t2 to be tau. So that basically says ek of t minus tau into ik hat of tau. This, I mean, this I can write it like this also, right? And basically tau times t minus tau. So if I choose t1 to be t minus tau, this becomes t minus tau and this becomes tau. So this of course only for one tau. You can do it for multiple values of tau and sum them up. So that will just be this. And last step, without paying attention to convergence, you interchange these two. And then you end up with so. Fine. I mean, this is how we can prove the same result in time domain. That's all. But the only thing I want you to remember, bear in mind is the moment you have inductance and capacitances, the reciprocity ratios you consider only in frequency domain. That's all. In time domain, only the convolved quantities are equal. Okay.
Let's say that the network, we have switches.
Right. Let's come to that later. No. Firstly we'll do LTI. We'll next go to LPDV. That's our.
The thing that you put, if the capacitor is not LTI, then it is not valid.
Right.
But if the network inside can be LPDV, then also this can be valid.
It will be slightly. We have to do some modifications. We'll come to that later. Right now, let's focus only on LTI. So the moment this has RL and C, you do everything in terms of the transformed quantities in frequency domain or Laplace domain. Let me just write C. So everything is in terms of j omega. Okay. Cool. And as I saw, as I briefly discussed in the last class, this reciprocity is actually very useful in practice, especially for calculating the transfer functions to find the power spectral density. So if we have an RLC network where we have multiple resistors, so let's say I bring out the resistors separately here to show. Say there are like million resistors here, and we are interested in finding what is the power spectral density at the output. And as usual, we replace a resistor by a noiseless resistor in series with the noise source Vn1. So here it will be say Vn2 and Vn3. You know that the power spectral density at the output is basically the first source power spectral density of it times mod h1 of f square plus so on. And basically to find each of these transfer functions, you'll have to consider only one of them, null the rest of them, find what is the transfer function and repeat it. But now we know reciprocity. So what we can do is basically de-energize all these noise sources. What you have to do? We need to apply a current and measure what are the currents flowing here, right? And basically if you apply e power j 2 pi ft as the current, here you will have h1 of f times e power j 2 pi ft, and similarly here you will have h2 h3 and so on. Okay, great. So this is fine. We have considered R, L and C's, but with just R, L and C's we can't make useful and practically relevant circuits. So what is the element that we need? We need transistor. Transistors are non-linear devices, but luckily since we are dealing with noise, the amplitude of the noise is really small, and in that amplitude range we can approximate the non-linear characteristics by a linear characteristics. So we can instead of considering the entire non-linear IV relation for a transistor, we can replace it by a small signal model. And what is a small signal equivalent? It's a voltage controlled current source, right? I mean, it can be a MOSFET, FinFET, BJT, vacuum tube, anything. or any crazy devices people make. For circuit design, it is a voltage controlled current source. That's all. Right? So let's see what happens to reciprocity with control sources. And first let's look at their VCCS, because that's the model for a transistor. So let's say I have a VCCS connected between nodes A prime and here it is B prime. So this voltage is VA and this current is GMVA. So let's say this is in a big network, and the network, in addition to this voltage controlled current source, has multiple RLNCs. Okay. So now, if reciprocity were valid here, if I apply some excitation here and measure the response, I should get the same response by just interchanging the ports where I am applying the input and measuring the response. Right? And again, for this to be true, the summation Vk Ik hat for the internal branches must be 0. Right? And one example where that could be 0 is if the branch voltage is proportional to the branch current. Right? So let's take the voltage controlled current source and see what happens. So let's look at this branch. What is the current in this branch? 0. So IA is basically 0. At least I can write it as 0 times VA. Right? What about the current here? IB? GMVA. And obviously it's not something times VB. So at least it is apparent that reciprocity as such is not going to be valid here. Right? But let's not lose hope. Let's try to see if we can make some modification here so that reciprocity result still holds good. Okay. So I mean, one thing is clear, that if I just have the same VCCS here, reciprocity is not going to be valid. Right. So let's say we are having some other element here. We'll find out what that is going to be. And let me just mark the voltages VA hat and this is VB hat. And we need to figure out what that is. Fine. And this element we have to choose in such a way that if I do the summation Vk Ik hat and Vk hat Ik, that should be true. Okay. And of course the network has multiple RLNC also, and you know, for the branches containing RLNC, this relation is fine. So we'll only focus on the branches where this control source is present. So that's basically these two branches. Okay. So let's write only for the branches A prime and B prime. So let's start. We'll start with the voltage in this branch, which is VA, times the current in this direction, which is some IA hat. Fine. Plus the voltage here, say it is some VB, times the current here, which is IB hat. This should be equal to the voltage in this branch, which is what? VA hat, times the current in this branch, 0, plus the voltage of this branch, VB hat, times the current in this branch in this polarity. What is it? GMVA. Fine. So if this relation is true, then our reciprocity result is also valid. Okay. So here, of course, VA, VB are all fixed by the rest of the network and this VCCS. So the only quantity we can play around this with are the voltages and currents of these two branches, because we have not decided what the element here is going to be. Fine. So let's We'll take it to next page. Okay. So this is 0. I'll just erase it. So I just have this. So I'll bring VA here. So I'll have VA times IA hat minus GMVB hat, fine, plus VB times IB hat, this is 0, fine. And as I just mentioned, the only control we have are with the voltages and currents VA hat and VB hat, sorry, VB hat and IB hat. So what can you, I mean, from here, if this has to be 0, what is one possible solution? Individually, if these two terms are 0, it is 0. And of course, to make this entire term go to 0, VA is not 0 obviously. So I'll choose IA hat to be GMVB hat. So that makes the first term 0. Next we have to make this term 0. And again, VB is not under our control. We have to choose IB hat is 0. Then reciprocity is 1. Fine. So let's try to see what circuit element will make us realize these these relations. So let me copy this. Okay, so the first thing we'll see IB hat to 0. IB hat is the current flowing here. This has to be 0. What do I do? Yeah, I don't do anything, let it be open. The next is IA hat, which is the current in this direction. That should be GM times this voltage. So what should I put? A controlled current source. And the trans conductance is still GM. Fine. Okay. So in the original network, between A and A prime, we had circuit like this, and between B and B prime, we had the control source, which was GMVA. But now you see that for reciprocity to be valid, we just need to replace this voltage controlled current source by the same voltage controlled current source. You just have to flip it around. Fine. So let me write it again here. So if I have a voltage controlled current source like this between A and B, here at B I will sense and then put the control source. Okay. So again, this is in a big network, and if it has RL and C, I don't do anything to this RL and C because by default they are obeying or satisfying the required relation for us. So you don't touch this RL and C. Wherever you have this voltage controlled current source, you replace it by the same voltage controlled current source but flip it. Okay. So now if I apply a current here, I1, and measure a voltage, and here I apply a current I2 hat, measure a voltage V1 hat. The ratio in transformed quantities, which is V2 by I1 of j omega, that will be same as V1 hat by I2 hat of j omega. Okay. So and this is called inter-reciprocity. And of course now the network on the right is no longer same as the original network we had, and this is called the adjoint network. So, do you guys know this adjoint operator for matrices? I mean, not the adjunct, I mean, not the transpose of cofactor, adjoint operator. Okay, yeah, I mean, yeah, this transpose of this whatever cofactor, it's actually adjunct. I mean, it got changed to adjoint, but there is an adjoint operator in linear algebra, and actually you can prove this inter-reciprocity using the matrix relations of the network. If you recollect, you can write for any LTI network the node voltages to be G times V from KCL, right? And if you start with this, still you can prove it. And it turns out if you do this adjoint operator, you can come to this network. So it's okay, I'll leave it there. And that's why this name is adjoint. And this was first proposed, I think, by Bote. I think some Greek. And he was a student of Tellegen, no wonder. Yeah. So now we see what we have to do. We have a voltage controlled current source, right? So let's see. That was a notation he coined. So yeah, if you invent something, you use Mike's theorem. It's okay. I mean, it's not the conventional reciprocity that we are aware of, but we do some modification. Reciprocity is valid, so he decided to coin it inter-reciprocity. That's all. Okay, so let's actually stare at this result once and understand it so that for the other control sources, we can look and say what should we have to do, right? So again, this is for the VCCS. This is a VCCS. This is the original network. Okay. So even in the adjoint network, we still have a VCCS. Fine. So if you think about it, let's say this is A prime, B prime. So in the first network, that is the original network, the across AA prime we were actually sensing, and in BB prime we were actually sinking or sourcing, so I'll just call it the output side, and we were sensing what voltage or current. We were sensing a voltage here, and in BB prime we are outputting current. So in the adjoint network, where are we sensing? In BB prime. So this is basically the sensing branch, and we are sensing a voltage, and in AA prime we are outputting a current. Fine. And if you think about it, we are sensing a voltage in the original network. In the adjoint network, we are outputting a current. This, both of them flipped. Similarly, here we are outputting a current, but in the adjoint network, we are sensing a voltage, right? So if you get the hang of it, let's quickly do for VCVS. So now let us say I have a VCVS. K times VA. So here I am sensing a voltage, and my output quantity is also a voltage. So here in the adjoint network, since I am sensing a voltage across AA prime, I need to output a current. Similarly, in BB prime I am outputting a voltage, so I should be sensing a current. So this is a VCVS. What this is? What is this? Current control current, right? So I have to sense a current that I'll do using a short circuit, and an output current like this. Okay. And the factor is still fine. So just to get a hang of it, let's derive this also once using our Tellegen's theorem, and we'll just reuse the expressions here. So now here we have a voltage controlled voltage source. Say the ratio is K. Here we'll have to find what we need to put, right? So again we'll do the same thing. The voltage here VA times the current here IA hat is there. Second is the voltage in this branch, which is K times VA times the current flowing here IB hat. This is equal to the voltage of this branch VA hat times the current in this branch 0, fine, plus the voltage of this branch EB hat times the current here, and we don't know what that is, so let's say that is some IB. So instead of G and VA, I'll have it. Fine. Okay. So let's take it to next page. So now this is 0, so I'll remove this portion out. So I'll have VA times IA hat plus KIB hat is this. So what should be chosen to be 0? To make this equality hold good, what should I choose? Yeah, first is no, IB you can't make it 0. IB is in the original. Yeah. EB hat is 0, and here basically IA hat is minus K times IB hat. Fine. So what does it result? Let me copy paste. So first is VB hat to 0. So here I'll have to, what should I do? Short circuit. And this is the current IB hat. Remove VB hat. Okay. And the next thing is across A prime, I'll have to ensure that the branch current is minus K times IB hat. IA hat is in this direction, so the current in this direction must be minus K times IB hat, or I can change the direction of the current and say that the current flowing up is K times IB. Okay. Fine. Of course, one trick to remember the direction of the current is for the adjoint network, everything is like this. Okay. So let me show that later. So we know that if we have a VC Vs in the adjoint network, we'll have to replace it by a CCCS. Okay. Similarly, if here I have a current controlled current source, I should replace it by a voltage controlled voltage source, right? That's all. And as I mentioned, currents, you remember it like this, right? In the original network, in the adjoint network, the currents are actually flowing. Good. So, what is the last element pending? We looked at VCCS. VCCS becomes VCCS, no change. Just the sensing and the sourcing nodes got changed. VCVS became a CCCS. CCCS became a VCVS. What is the last source pending? CCVS. So this is CCVS. So let's say there's some RM times some IA. What should this become? Same, right? Here I am sensing a current, right? So it should be outputting a voltage. So I'll be outputting a voltage. Here I am outputting a voltage, so I should sense a current. That's all. If this is some IB hat, this is the same trans resistance Rm times IB. And of course you can derive this just like how we derived for the voltage controlled current source and voltage controlled voltage source. So you can try that as an exercise. So just to summarize, if you were to apply reciprocity for networks containing R, L, C and control sources, the original network has to be replaced by a network called adjoint network, which we'll call N hat. And if the original network had R, what do you do in the adjoint network? You don't do anything. The branch is retained as it is with the same resistance. Same holds good if you have L and C. Right? Now, if you have a voltage controlled current source, this direction, what do? What should the element be here? The same voltage controlled current source, just the sensing and sourcing nodes are flipped. Fine. This is also a VCCS. If we have a VCVS, here I will have a CCCS. So this side is short. The current flows this way. Similarly, if this is a current controlled current source, this will be a voltage controlled voltage source. And lastly, if it's a current controlled voltage source, current is sensed like this and voltage is output like this. This will also be replaced by the same current controlled voltage source, just the element is flipped. Okay. And I mean, we should be aware of the direction of currents. So we can remember it like this for the adjoint network, whereas for the original network, the current is this. Right? This is clockwise, whereas for the adjoint network, it is counterclockwise. And in fact, this concept of adjoint and inter-reciprocity is what is used by circuit simulators for actually computing all the noise calculations. And yeah, we'll stop it.